guess you know Leslie Lamport, AM Turing Award winner. He said, people try to learn programming by being taught how to code. Then they are being taught writing by being taught how to type. So rather than spending lots of time learning how to code, we should understand the idea of mathematics behind it. The first question: how do we describe computational devices? We describe it by all their possible computations. For example, the first simple computational device was the clock. It has just two states, 0 and 1. So possible computation is time interval it can tell depending on its frequency. Now we will see different roles and their contributions. First is a computer scientist. They give a mathematical model and possible computations it can do theoretically. Hardware designers take this model and depending on the need, they design efficient hardware for applications. Software engineers take hardware specifications and its power and make system software as much as possible. Here are different computational models in chronological order. First is a calculation by hand. Here, the hand and the rules of calculating the sum are our computational devices. And it can calculate sum or difference in the range of 30. Abacus was used in 5th century BC. It was good because it can calculate sum and differences and also multiplication up to 10 raised to power 6 to 7. As we have seen before, we define computational model by the number of possible computation, and in this case, very few computations, so less power. In 1866, we had logic gates, and by using their different combinations, we could map a different input to its output. This model is useful when we have constant bits as input, but large inputs make this machine complicated and hard to design. In 1936, Alan Turing described a different model. It has all power that we need. Formal definition you can find in the link in the description. For just an overview, it has a word tab with symbols and pointer pointing to one of its entries. This pointer can be defined by a function that takes entry and states as input and new states left or right tag and the right symbol as output. For example, in this case q1, 0 are input and q2, 1, r are output. Here we got r symbol, so the pointer will go to the right entry and write 1 in the current entry. But how actually it can calculate sum or calculating pi? For example, if we want to calculate 2 plus 3, then this step will show this array initially. We will define this pointer function such that it will print 5 in binary after completion. Now this machine can do all computation we can think of. For example, calculating pi up to 1000 digits and calculating other complex mathematical expressions. Church-Turing thesis. It says all other computational model you can think of are equivalent to Turing machine. If you give another model of computation, then it will have less or equal power than the Turing machine. We can answer the more exciting question with this thesis. If the thesis is true, then we can tell human brain is also Turing machine, because after all, Turing machine is creation of human mind. Only Turing machine can simulate Turing machine. Second, AI can achieve high speed or performance better than humans, but it can never compute what humans can't. If someone finds a better model than the Turing machine, it will be called Oracle. We have seen theoretical models and have the best computational model, Turing machine. Hardware designers may choose to model it by mechanical model, electrical circuits, or optical computing. The electrical model is the fastest. Research is going on for the optical case. These models are theoretically equivalent to Turing machines, but different features are added to compute faster. In modern processors, we can compute single instruction in constant time. Memory access in constant time. Here RAM and disk are work tape and processor you can think it as pointer of Turing machine. For example, we have simple C code. After compilation, it will be in binary form. Now the code will run sequentially. It can also jump directly to another location because we have constant memory access. After completion, it will print output in output buffer or change the state of some files or do not do anything, depending on what code we wrote. Here, hardware designers can choose fast access or fast computation on the basis of use of the hardware, but changes are made such that it proves that the model is still equivalent to Turing machine. However, if we use this architecture, we have to load our programs again and again manually. So we need an extra layer that maintains all the hardware. So for that, we have one code we call the operating system. Compiled code of it is in memory and runs on processor until we power off the device. So now, our pointer will jump between user code and operating system segment code to complete our purpose. But how does it solve our problem? Now OS code have features to load user program, and we can use input devices to give instruction to load user program in main memory. So operating system makes easy to maintain hardware resources. Programming languages are built on the concept that we have one state of the system at a time and we change it by defining rules. A number of iterations of this state change are too large, so we need computers to work for us. So when we write code, we should not think in terms of language, what it can do or what it can't. If we write algorithm by defining initial states and its changing states rules, then it will always be implemented using any language, because after all computers are Turing machines.